Okay, so this indicates that this input is B. This is A. This is the wire which connects A to the OR gate, and then A is also connected to the NOT gate, and out comes C. And then this is fed to an AND gate. And then the output of C is fed back to this AND gate. So this is D. Okay, so this is what I would call a more complicated circuit involving logic gates, which involves multiple types of gates. And so the question here is, one, write a Boolean expression. Boolean expression is the same expression I wrote down earlier. A times B, A dot B, A plus B, and so on. So write a Boolean expression for C and D. In terms of the inputs, in terms of A and B. That's part one. Part two is draw the truth table. Yeah, I also showed you how to draw a truth table, right? You take all the inputs, all the combinations of inputs of A and B, and then you write the expressions, answer for C and D. Okay, so let's see how to do this. So let's look at C first. C is essentially, the output is the output of an OR gate. So we can write C as A plus B. That's not hard, right? Pretty straightforward. Let's look at D. Now, what's happening to D is this. We have A is the input to the NOT gate. What comes out of the NOT gate is A complement. And what goes in on the other leg is C. But we know that that gate is an AND gate. So the inputs for the AND gate are C and A complement. So we have T equals C dotted with A complement. Just what is, I just wrote the dot product for the AND gate, and then I took the right inputs based on that items shown in red, right? So now we can further simplify this. A plus B Hilda. Okay, it turns out that it doesn't really matter how you multiply this. This does not have any, it's not like matrix multiplication where the product matters. So you could invert it, it's not a problem. Now you could technically simplify this, like when you take, I've not really talked about that, but you can actually expand that bracket out, and there's a distributive property, which means that you can actually distribute this A like so. Well, this should be to be consistent with the expansion. And then what's A dot A complement? It's 0, right? Because if A is 1, A complement will be 0, or vice versa. So this will always, so you could technically simplify this as A complement dot B, or keep it as the first equation, but there is value in simplifying, because if you were to build the circuit, right, would you build it with what do you need to build the circuit? Well, you need inverter, right, for the bar. You need an AND gate, and then you need an OR gate. So you need 3 gates for this expression, but for this expression, you need 1 inverter and 1 AND gate, which is convenient, right? So you've reduced, by simplifying, you've reduced the complexity from 3 gates to 2 gates. And that's nice because it's very easy for me to write these things, but if you could build this out of wires that you better write the simplest expression possible. Okay, so now let's get to the truth table. Truth table, remember what I wrote down for this: C equals A plus P, and D equals A complement times P. Okay, so we'll write this in one shot. What I mean by that is we'll just write A, B, C, and D in one place, and then fill it up 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. So C is A plus B, 0. 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 1. And for D, we have A complement times P. So A complement is 1, but times 0 is 0. 0 complement is 1, so this will be 1. 1 complement, this will be 0. 1 times 1, this will be 0. Okay, now, if this is hard for you, I just wrote down them quickly, but if it makes it easy for you, you can also do this. Just write A complement. A complement is 1, 1, 0, 0. And now all you have to do is, take the dot product of that. Right? You see that 1 times 0 is 0, 1 times 1 is 1, 0 times 0 is 0. That's one way you can do it. The other way, remember that what was D? It was C dot A complement. You could also use this fact. That is, now what you'll have to do is you'll have to take C and A complement, take the dot product. So 1 times 0 is 0, 1 times 1 is 1, 0 times 1 is 0, 0 times 1 is 0. So it depends how you want to do it, but all ways we do it, you get the same answer. So this is right. Okay, one more question and we'll stop. Okay, this is going to introduce you to a timing diagram. Okay, so here's an example. Let's just take the OR gate. Okay, we wrote the truth table for this: A, B, C, 0, 0, 0, 1, 1, 0, 1, 1, and output would be 0. So it's sum, right? So C equals A plus B. So we have 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 1. And the timing diagram is this. We show this same logic, the truth table, as a graph. This truth table as a plot. Okay, what is A and B? A and B is input, and C is output. And we've seen how to draw inputs, outputs in I don't know, diodes. We had done that, right? Where the input also in op-amps. So we can actually draw it in this fashion. Okay, so A, B, C. Call this 1 and 0, 1 and 0, 1 and 0. Okay, so let me draw. I'm going to try to draw this column. Okay, so 0, 0. So 0, 0. Then it goes 1. Then another 1. Right. Now let's do it for B. B is 0, 1, 0, 1. So 0, 1, 0, 1. And then C is going to be this one, 0, 1, 1, 1. So you could either do that, which is you already wrote the truth table, you can do that, or you can actually just look at the timing diagram. So you have A plus, you need to do A plus B. So 0 plus 0, which will be 0. 0 plus 1 will be 1. 1 plus 0 is going to be 1. 1 plus 1 is going to be 1. So this would be a timing diagram. Okay, so this is how I would do it by hand, but if you want this to be done in a device, a physical device, then the device which will do this for you are timing diagram can be obtained using either multi-input digital oscilloscope, multi-input oscilloscope. There's another circuit called an logical analyzer, which can be used to get these timing diagrams. Now, the reason why we're talking about this is if you don't have access to an Arduino, you can actually wire up circuits on and off by using these gates. So, for example, when you, I don't know if you've seen this lighting where you have two switches, but both those switches basically turn something on. So you can basically have logic which basically does this without having to deal with Arduino. You don't have to program. You can actually make the device smart enough to do things by using logic, right? You don't really need to write programs. So before people had access to microcontrollers, this is what you would do. Without microcontrollers, you could just build it up. Small circuits will do that. That's probably cheaper than to do, and it is because every time you have a microcontroller, you need to now it's $15, $20. One of these gates would be like a few cents. And so if you want to mass produce something like this, you're better off just building the circuit from ICs rather than trying to buy microcontrollers and hooking them up. Also, the current draw in something like this is minimal compared to a microcontroller. Microcontroller, you need to power everything up. So there are some advantages of using digital ICs. It's not like it's totally useless. Okay, so I'll stop and I will see